later.
Okay, this is Friends with Fridges,
Mystery and entanglement. What's
featuring
that?
David.
Inequality.
Entanglement.
So you will be. I will give you what is just the bare bones outline of a presentation which Gary can follow up with after some email correspondence, which is in the making. It's actually out there in the internet web.
Interweb.
It will arrive having gone around the solar system for
Will it still be the same when it gets there?
It will not be the same as this. It will be much improved.
No, but
Okay, but this is the outline, and this is also attempting to allow science to converse with the humanities.
Ooh,
Which is why you're getting the very brief version tonight.
awesome.
Hang on, what's that symbol between them?
Oh, it goes both ways.
But is it
Because
a...
the humanities should inform the scientists.
Okay, so it's not an
What's really
it's
important in life.
Okay. Yep.
So, first of all, there's a mystery, and I won't be able to illustrate the mystery very well, but I found information on Google, YouTube, internet site, which has a fantastic example of a mystery.
Huh.
So basically what happens is the unexpected. So it's counterintuitive. Something's happening that is counterintuitive. So I cannot secure your curiosity by just telling you that there's a mystery, but you have to believe that it can be demonstrated in something that's so simple that you'll say, okay, I want to follow up on this. And that's in this video that Gary will have at his fingertips a little bit later this week maybe, and certainly within the next 2 weeks. So, first,
Even the MBA.
please accept that there's a mystery. The second thing is there's a book by Adam Becker, which both Gary and I have read, or at least securely browsed. And the title is
I read it too.
What is Real? Gary and I are real. But we still thought that there was a question that needed to be answered properly. And while Mr. Becker understands a hell of a lot more about this than we ever will, he did not give a very explicit example of something that he describes very thoroughly up to a point, called Bell's inequality. But before we get to Bell's inequality, I want to pause to take a side trip to something called entanglement. And entanglement is something that there's been a long-lasting dispute in physics between Einstein and later physicists and others. But this concept first was mentioned, and the word translated from the German to exactly entanglement, by Erwin Schrödinger. Famous because of allegedly having concerns about the survival of a cat. But in this case, entanglement was just mentioned in passing because it was something that Einstein was kicking around in 1935, and Schrödinger paid close attention to the literature, and he said, there's something going on here that I think is a bit strange. A mystery for Schrödinger is still a mystery for us. And in 1935, he said, I think there's the possibility of particles, subatomic particles being entangled, and that the presence of entanglement is something that we might consider. And he sort of gives the concept. Einstein says, this would be very strange, and I don't believe it's possible. I don't
1935.
believe that entanglement exists.
Was it 1935?
In 1935, there
Wow.
is this debate,
Yeah.
and it's an unresolved debate until 2015. And in 2015, an experiment is done to the satisfaction of most critics that shows that entanglement exists. exists.
But
But
2005.
I
15.
digress,
15.
and I've actually
Wow.
given you the conclusion to this discussion. However, before entanglement could be pursued seriously, and for many, many years it was viewed as being, so much against the classical physics concept of the world, that if entanglement did exist, it would just blow a hole in the middle of it. So most physicists were taught that this was a kind of an idea, but it didn't have legs. It didn't carry any merit.
Are you going to say what entanglement is?
Well, I will.
You will. Okay, you're just teasing us
But-
at the moment.
Bell,
Tease.
Taunting. They're being taunted.
I just wanted to mention
Tease.
Erwin Schrödinger, because
Yeah,
I'm name dropping.
Don't
And
say
I dropped Einstein's name as well. But then we get to this Irish physicist called John Bell. And John Bell became much more important to the world of physics because he helped the Large Hadron Collider develop the experiments needed to show the existence of the Higgs boson, which was
God
only
particle.
discovered in 2018, I think. When they first
2017.
Might have been 2017. So Bell has died, and he no longer is no longer eligible for a Nobel Prize. He dies too soon. But
Shame.
he
Shame.
shows a experimental. He shows the design for experiments which would be able to distinguish between the two sides of this physics debate. The classical physics said you could not have something called entanglement. The quantum mechanics said, yes, entanglement is definitely a possibility. So you've got quantum mechanics and quantum theory of physics that is running up against the classical traditional physics.
Sounds like
So
much
what
of
is
history.
so as Gary says, get on with it.
He's
What
verbaling me.
so we'll get back. We'll get back to the science and humanities, but let me give you the humanities interpretation of what's going on.
I like this, David. This is
Make
good.
us cry.
Excellent.
So let's say you have two particles. Two particles. We'll call it one and two. Actually, they could be photons, they could be quarks.
Sorry.
The Bell's inequality has been demonstrated for a number of different
You're on
particles.
detention. Sorry.
Sorry, David.
Send him out.
Two
Send him to the
particles.
headmaster.
And
I'm watching.
Could be electrons.
let's say they have had an encounter. They've met. So
Physically.
Yeah.
Well, let's not worry too much about
alright.
physicalness because it's the real world we're talking about. So these are two photons. They've been together, and then they're going to get separated. And I was going to say, in the humanities version, it would be like two people coming together and having an experience. And
Conversation.
then we're going, could be whatever. It might be you shared a recipe. You might have sat at this dinner table and had a conversation.
Yep.
Or you might have been like Bruno and Gary, who were able to come to their own home and dial up the other guy's music collection and find something they liked. Why is that?
Wow.
They had something going on between them that was
Something.
that they're not just random particles. They met and something happened.
And they would
Okay,
change.
so then the question is,
You knew you were special.
Everyone's special.
these guys get separated
People are more special.
and
What do we got there? Mu.
They're separated. If you pay
they
attention, you
get
hear.
separated, and then we have something happening over here, and we'll call this a detector.
You watching this? You getting this?
I'm getting a detector. I've got
And then there's another
Measurement
detector down
Great
here.
detector.
I don't have to write detector twice because
No.
I'm using color.
Yes.
So you can see.
Got it.
Is
And
there
we're
any
intelligent
colorblind?
beings.
Okay.
Detectors in
So,
green.
this is
Gary
green
is.
and this is green. They-
But wait, they're going to miss the detectors because they're going in the wrong
Wait a
direction.
second.
Sorry.
Well, they haven't gone anywhere yet. They've just gone off.
Okay.
And we are going to have them come to a detector. Each of them. We are going to communicate. we are going to detect. We will see something at each of these detectors. This is the science. But the human side of it is these two particles that did have an engagement, while they may be widely separated. Widely is to be defined impressively, but widely separated, they will still care about what happens to the other.
Ah.
Oh, it's very
So
much
there's that
humanity.
sense of
Very much humanity,
something happens to the one and the other gives a shit.
Knows already.
Well, might even
Maybe.
Verbal,
Mike.
just verbal back.
he's stealing the fucking show.
He is, isn't he?
I'm gonna have
Shut
up.
You're still in the fucking show. Go sit down in the back row.
Di, you're about to go to sleep.
Come on. Live it up.
That's a forecast. So these two go off. Something happens here, and the other is able to respond to what happens here in ways that Einstein said could not happen. And so now we're going to have to go to the science of it. But that's sort of the humanities version of it. Two things interact, they go widely apart, but somehow they are able to be informed and respond, and I call it caring.
Yeah.
Okay? But then the question is, well, how the hell does that happen?
Good question.
And physics
I would have
says
asked that question.
it doesn't happen and cannot happen and it will never happen. So just don't waste your time with that. We're going
Because
to
it's
go off
come
and
from-
build an H-bomb.
Yeah.
That's what is made very clear in this book.
Oh.
That the whole program of physics was
right.
so controlled by the U.S. military and the Russian military, and the money was flowing to the military, and because they said quantum mechanics works, we can build bombs with it, and it was true, and it was, and it did. So it's very real stuff.
But it could do a whole stack of
And-
other things.
But this level of understanding of why quantum mechanics worked was incomplete. Like we
Just
don't.
erase the
We don't know why quantum mechanics works, but here's your bomb. And so nobody was really dealing, very few physicists were dealing with, I apologize, I think I'm going to be buying
We invited this. It's good.
It's good. It's lovely.
Maybe this
It
could
looks
be
like a
damaged in
bomb.
your Renault.
No, we love it. Every bit is.
Okay, so Bell's inequality is the first proposition that allows this mystery to be adjudicated. And Bell's inequality said basically that if you separate two particles very widely, that they will, when detected, their characteristics will only be similar up to a certain limit. It cannot, and they will only be certain. They will. Their characteristics will only be matching up to a certain limit, and that probabilistic limit would be 1/2. Half the time or less, their behaviors would be similar.
Wow.
And that's the traditional physics proposition.
How did they come up with a half?
Well, it because the particle physics theories allow for things like a characteristic called spin. This is the example that I would pursue because it's the one that we've got some data on from Wikipedia. So
we all trust Wikipedia.
It's the spin characteristic.
Yeah.
So you could say that it could have been the charge of an electron versus a
Proton.
electron negatively charged, and a positron, I guess, might be a positive charge. I'm not too sure about that. But you can find there's negatively charged particles and there's positive, and if they switch, then
It's 50%.
which at the detector, what was
it's
the
like
charge?
NMR
Was
stuff,
it a
isn't it?
positive charge or a negative charge?
It's just black and white.
Yeah, but most particles have these on-off characteristics. They're
So
not
it's
like
binary. They're binary.
Yeah.
We used to look at it in nuclear magnetic
Binary,
resonance
nothing in between.
of particles.
Okay.
And
As far as we
So-
know.
No.
The example that I have found for the full lecture that Gary will be giving later this month.
Yeah. What's in between?
I like that spin.
Good spin, David.
half-spin particles have, there's some data in the results. So a quark is an example of a half-spin particle. And we've all heard about quarks.
Oh, yeah.
We don't know them, but they're the fundamental particles which allow neutrons and
Electrons.
neutrons and protons. Thank you. I kept thinking of positron. So the quarks are the constituents of neutrons and protons, and with quarks you build atoms, and with atoms you build molecules, and then you get the table of atomic weights.
Atomic. Yeah.
But, okay, so now we get back to the physics of this. The Bell's inequality said, you can expect to see the behaviors of separated particles at detectors showing certain similarities, but only up to a point. And in the case of half-spin particles, we'll call this the classical physics hypothesis or theory says that the measured correlation, so we'll call this correlation, has to be less than, or, and they don't say less than or equal, I think it's actually absolutely less than 0.05, 0.5. So that's a Bell's inequality for half-spin particles, and I trust that the Wikipedia entry that shows this piece of information is the one is trustworthy. The quantum mechanics, physics will allow for correlations which are in excess of that. I don't know what quantum mechanics says about the correlation being at an extreme level of a certain or less. Bell's inequality says with classical physics it has to be so. But quantum mechanics allows for some different number, higher than. So the empirical finding, or the result, which has been found experimentally in the case of half-spin particles, is that the correlation is in the vicinity of 0.7. So the fact that quantum mechanics will allow for the higher correlations, and the classical physics says it cannot possibly be higher than 0.05 according to Bell's inequality.
That sounds like it's important.
So this is crucial because Einstein said you couldn't have anything called entanglement. But with entanglement, particles that have met are able to somehow be coordinating with one another in ways that cannot be consistent with the laws of physics as stated by, or as taught and traditionally is the sort of dominant story. And the full description that is probably in here as well as on the web is that it's called classical real local. So
Local being what?
reality, I guess. Local reality.
Meaning
So-
it's physically contacting?
Well, what it means is that, as Einstein called it, you cannot have action at a distance. Spooky action at a distance.
Somebody called it.
Well,
that was what the
allegedly.
experiment results implied.
So,
Because if you measure one particle here and another one somewhere else, once you measure that one, you know what that result is going to be, even though it might be light years apart. And that information can't travel. It was so far apart that information couldn't
so
travel
speed of light enters the
in
picture here.
in a short enough time.
Yeah.
It's really hard to describe.
So the
isn't it?
experiment that gives this result is one where one detector might be in Los Angeles and another detector is in London, England. So what you do is you get your quarks together in a collider. You create a pair of quarks from some sort of atomic collision, and you send them off into different directions, single quarks, single particles, and then they pass through a detector. And these detectors are coordinated, or they are
Calibrated?
Calibrated, thank you. They are calibrated in such a way as that there's no way for them to be in communication with one another when they detect what happens to these quarks. Is this quark a spin up or a spin down quark when it arrives? And probabilistically, the classical story is they will not be their spins will not be correlated more than 0.5. But their spins are in fact found to be correlated at a level of 0.7.
Which means there's something else happening.
Well, it means that
Once you
We don't
measure
know.
one,
it's
the other
you
one
can
knows
choose
it's been
reality or local.
that's the implication.
And what Einstein said, if science can't say that all physics is local, then we have no easy way of conducting all the experiments that we are so dependent upon. Locality here has to do with the idea that only the circumstances immediately surrounding and present at the time a measurement is taken are the only circumstances that matter, and that the fact that there might be measurement made of one of these quarks at one place should not influence on the measurement of the quark that's widely separated. And if the quarks cannot communicate with one another, like, here's what's happened to me, then it's got to be something much more subtle, like a wave that somehow each quark is floating on the same
Some
wave,
Other
and that
fabric
the
that we
wave
don't,
exists, but we can't detect.
we don't know about
It's
it yet.
faster than the speed of light.
And it has to be a presence other
yeah.
than the communication because speed
And
of
it's
light
not
is the-
neutrinos or anything like they can't even go fast enough, can they?
No, nothing can go faster, and so there cannot be any communication faster. And they said that this, another part of the